Okay, so good afternoon, everybody, and good morning. It is my pleasure to introduce Dr. Karen Livesey, who will be, graciously accepted an invitation to basically repeat something she did this summer, which was a tutorial on magnetic nanoparticles. And I've known Karen for years now. I don't remember how many years, primarily through conferences, and also through her work in the area of magnetic nanoparticles. And it's not going to be the standard introduction where people read a list of accolades or where people did their PhDs and all that. I'm just going to say that hopefully this is a very fitting introduction. I've always loved the way she explains things. When she presents her research, it's always very clear. She is an excellent educator in addition to an excellent researcher. Her own research in the area of magnetic nanoparticles has applied modeling and theory to help us better understand a lot of things that we do in the laboratory. And one of those is a paper on how to interpret, magnetic measurements that are very common in the literature and very commonly misinterpreted. I'm just going to leave it at that.
Okay.
I encourage you to. I think she's going to mention this in the tutorial. Karen gave this tutorial at the Magnetic Carriers meeting in London this summer, and I thought it was phenomenal, and I wished all my students could see it. And so that's where the idea of recording these came about, and so I'm really happy that we're finally doing this. And so with that, I'm going to leave you with Dr. Livesey. Thank you.
Thank you. That was a lovely introduction. I think it's about the most personal introduction that I've had. So that was great. Thank you, Carlos. And thank you, Carlos, for setting it up. We hope that these tutorials will be of benefit to lots of people in the field. So recording them means I don't have to give them again and again, but people are still welcome to reach out to me if they've got any questions. So the tutorial split into 3 parts. And so I think we're going to meet 3 times, and no worries if you can't come 3 times because they will be recorded. And so today we're just going to focus on part 1, which is basics and energies. And then part 2 will be on dynamics, and part 3 on characterizing magnetic nanoparticles. As Carlos said, I'm actually a theorist, but I actually like to be dealing with real data and helping people understand what's going on. So that's important to me. Carlos will be monitoring the chat, so I won't look at the chat, but he will stop me if something is really important and needs to be explained along the way. All right. Now I've got to make sure I can navigate through. There we go. So as I said, we're going to focus on just basics and energies today. So what makes a magnetic material magnetic? This is the first thing we should address. And the simple answer, perhaps too simple, is they have electrons. And electrons typically have magnetic moments. There's 2 sources of this magnetic moment, but one of the easiest ways to visualize it is, can everyone see my cursor there? Okay, so if you imagine an electron orbiting an atom, so the electron's actually orbiting this way, and that means there's a little current loop. Conventional current, unfortunately, goes the other way as the motion of the electron. We've got conventional current loop. We know from first-year physics class that a current loop gives rise to magnetism, gives rise to a magnetic field. So moving charges gives us a magnetic field. And that field that's produced by this current loop looks almost identical to the magnetic field generated by a bar magnet. So here's my little north and south pole, and I've got these curly dipolar field lines here. So imagine those same field lines coming out of the current loop, and then we can define a magnetic dipole moment, this mu here, which has a magnitude and a direction coming out of the current loop. So because materials have electrons, they have magnetic moments. Now, not all materials have a net magnetic moment, but we'll get to that. But this is at the root of why materials are magnetic. So here I've defined this mu, this atomic magnetic dipole moment, more carefully. So it is a vector. It's got a vector hat on top of it. And it's given by current multiplied by the area of the loop. So if we could figure out the current of this electron orbiting an atom, and we know the area of the loop, then we multiply that current by area and we get a quantity which has units of amps meters squared. And I really want to be careful with the terminology here. I really want to be careful calling it an atomic magnetic dipole moment, because we're going to have other dipole moments later. So this is the atomic dipole moment. Obviously, this is a very simple picture. If any of you have done any quantum mechanics, you know this picture of a point particle orbiting around like a solar system is not quite correct, but it will do. It gives us this explanation for why there is magnetism. Now, we've got more than one atom in a material, and if we have a ferromagnetic material, what happens is all those atomic dipole moments line up with each other. So I've drawn that here with a cartoon. The yellow block is our material, and all the atomic dipole moments are lining up in the ferromagnetic material for reasons we'll discuss in just a second. So we say that this material has a net magnetization. And the magnetization is found by summing up all of those dipole moments and then dividing through by the volume V that they occupy. Okay, so we sum them all up, divide through by volume. You can imagine this gives us the strength, how magnetic a material is, because if all its atomic dipoles are lined up, but there's only 4 of them in a volume of a meter cubed, that's not very magnetic. Whereas if we have a high density of these magnetic moments, then we have a very magnetic material. So the magnetization is given typically by big M. It's a vector quantity again. And what we do is we sum up all these atomic dipole moments in a volume, divide through by that volume, and that's our magnetization. And the units now have to be amps per meter, because if you remember the previous slide, the atomic dipole moments are amps meters squared. We divide through by volume and we have amps per meter. And I should say I'm going to try to use SI units wherever I can through this talk. Okay. We have other types of magnetic ordering. There's a lot of different types of magnetic ordering. I just want to mention one more, and that's because it's important for a lot of the materials we use in nanoparticle research, for example, magnetite. This is a ferrimagnetic ordering. So you can see that every other atomic dipole moment is up and the ones in between are down. But the down ones are not as big as the up ones. So we still get a net magnetization. We still have some net magnetism. So again, we can write down the magnetization. It may be weaker, say, than a ferromagnet, but we still have some net effect. And if we were doing some measurements of this material, we might not even realize that it's ferrimagnetic versus ferromagnetic, because we might not be able to tell that atomic dipole distribution. Okay, back to our ferromagnetic materials. And I said I'd explain why these are ferromagnetic, why all the dipoles want to line up. And it's because of an effect known as the exchange interaction. And I should say as well, when I say ferromagnetic materials, this is what in lay terms people just call a magnetic material or a magnet. So we're talking about iron, nickel, cobalt, and alloys of those, some rare earths as well, which are more exotic. So when people say magnetic material, typically they are talking about ferromagnetic materials. So let's talk about this exchange interaction. It's quantum mechanical in origin. It's actually a really hard effect to derive. My final year quantum students, we talk about it a little bit. So for us, we're going to just be happy to say it is the energy between neighboring atomic dipoles, which forces them to line up. So this exchange energy is at a minimum when the atomic dipole moments line up with each other. Okay. All right. But in reality, that only happens when our ferromagnetic material is at 0 temperature. Okay, so here's my cartoon again, but this time I've written above it T equals 0, because this is really only our picture if we could get down to absolute 0. And really, we're interested in dealing with materials at finite temperature, room temperature, body temperature, and so on. So imagine now heating this up, and the effect of temperature in all physical systems is basically to give us some disorder, to start jiggling things around, whether it's a gas or a solid or a system of atomic dipole moments like what we've got here. So imagine these now being able to jiggle. There's some thermal energy, some energy to mess up the nice ordering that we have. And so this is a better picture of what's going on in a real ferromagnet. So I've just made this cartoon. It's not precise, but you can see all these atomic dipoles are more or less aligned, but there's some different angles in there. And this is just a snapshot at a certain time. At a later time, the jiggle could mean that they're all doing something slightly different. So, as I said, this is finite temperature, temperature greater than 0. So here's a quiz for the audience. What do you think that does for the magnetization of this material? I can't see the chat, so you might have to unmute if you want to answer. And I know everyone wants to answer. Everyone loves, you know, the audience participation part.
Decrease?
Decrease, yes, very good. So you can imagine adding up all these vectors, and now I'm going to get a decreased sum. So the magnetization should actually go down as I heat up my magnet. And I can actually get to a point where the thermal energy greatly outweighs the exchange energy, and then all order is lost. So let's see that rather than me hand waving it. Here is a plot I took from an article, mainly because it is of magnetite, which is often our material of choice. And this is the magnetization in some units I don't want to tell you about. And here is the temperature on the x-axis. And so you can see I start out with quite a high magnetization in these units that I'm not telling you about. And then as I heat it up to, say, 820 odd Kelvin, the magnetization goes down. And then after this point, the magnetization has vanished. And this critical temperature where the magnetization vanishes, this is known as the Curie temperature. Okay. And I'm going to put some cartoons over this so that maybe it's easier to understand. At the lower temperatures, we have this ferromagnet where the dipoles are more or less lining up. There's some jiggle, so it's not perfect. And then above this critical temperature where order is lost, we say that the magnet is now paramagnetic. And so we still have these atomic dipole moments, they persist, but they're pointing in all different directions. And so the net magnetization is 0. Okay. Now, I just want to make note of this temperature here, 820 Kelvin. This Curie temperature for magnetite is quite large, and most of our measurements are done way below this. And we do see a loss of magnetization in nanoparticle systems, but for a different reason. So this is true. This is really nice for bulk materials, but for our nanoparticle materials, we're going to be working down here. And as I said, there's going to be a different reason why we lose magnetization in nanoparticle systems. So we want to keep going and exploring different energy contributions through the rest of this tutorial. So far, we've done exchange and we've talked about thermal energy as well. All right, and I should say as well, notice the exchange energy is in competition with the thermal energy here, and exchange is winning down here, whereas thermal energy is winning up here. And this idea of different energy contributions being in competition with each other and that explaining different physical phenomena is a theme that runs through this tutorial. All right, so let's actually make it a nanoparticle now. So as a theorist, this is my picture of a magnetic nanoparticle. It's a ball with some dipoles in it. We're looking at something, say, 10 to 30 nanometers wide in the magnetic core. Could be smaller, but that gives us a ballpark. So say 40 to 120 atoms wide, just to give you a feeling for this. Now, because we typically make these nanoparticles out of ferromagnetic or ferrimagnetic materials. And because they're so small, all of those atomic dipoles are basically lined up. So we're going to replace that picture with all these atomic dipole moments. We're going to replace it with one moment, which I'll call M this time, little m. And this we're going to call the macrospin magnetic moment for the nanoparticle. So I'm replacing all the atomic level details with one particle level moment. And this is commonly done throughout the literature. It allows us to make calculations and do fitting a lot more easily than considering all the dipole moments in a particle. Okay, there are some instances where it's not a valid assumption, but for most of what we do, it's a very good assumption to make. So I've been very careful with the definition again. My macrospin magnetic moment, little m, is given by the volume of the particle multiplied by that magnetization we've talked about so far. And this gives us units of amps meters squared again in SI units, okay? But it's different from the mu, the atomic dipole moment. It's typically going to be a lot bigger, okay? Because it's a bigger volume. All right, and then I said in the conference, some of you guys have heard all my gags before. This is my one slide for the chemists, and we're going to visualize this magnetic ball as having some ligands around it or some surfactants around it, and this will stabilize them in solution. So they're there and they're very important to consider, but we're not going to talk a lot about them in the tutorials. If you've got some questions, say at the end of the free tutorials, we could talk about what the ligands do, but they're not playing a significant role in the magnetism of the particles, so we're not going to talk about them at length. Okay. So most of the particles that we will deal with are known as single domain particles. And what that means is all the atomic dipole moments are lined up in the particle, like the picture I just showed you before. And say for magnetite, that single domain limit is typically for particles less than 50 nanometers in size. If we make particles that are bigger, what happens is we start splitting the particle into two or more regions where the atomic dipole moments are lined up in different directions. So this is a picture of two domains. And I've just drawn, two big regions where the atomic dipole moments are aligned. But remember that microscopic picture where all the atomic dipoles are underneath this big arrow, okay? And then if we go even bigger to something that's sort of macroscopic size, I can get all sorts of domains, okay? Now, the reason these domains form, and we should be aware of them because if we ever make big particles, they're likely to occur. The reason they occur is to minimize energy known as stray field energy. So I'm going to show you a picture which is very famous because it's in a textbook by Cattell. So some of you might have seen this picture before. We've got a magnet here, and we've got scenarios where it's split into a different number of domains. So here, for example, there's just one domain, and we see that dipolar field we talked about earlier. That has a lot of stray field energy associated with the creation of that dipolar field. If I split now the magnet into two domains, you can see I have less stray field, and that pictorially is showing us that we have less stray field energy. So we've decreased that energy contribution. And I could keep splitting into smaller and smaller domains. You can see with these two, these are what we know as closed flux loops. There's no stray field emanating from the magnet at all. So we really reduce the stray field energy here. But there is a trade-off. There is a competition, as we talked about earlier. Well, it's on the slide, so I won't ask you if anyone knows which energy is being traded off with. The energy that is now increased in these two is the exchange energy, because now we have atomic dipole moments along the boundaries of the domains, which are not parallel to each other anymore. So say from here to here, we have atomic dipole moments that are anti-parallel. So we reduce stray energy, but we increase the exchange energy. And this competition between those two types of energy might mean that in a bulk magnet, we end up with something, say, in the middle. Okay. All right. Enough about stray field energy. Let's talk about one that is really critical to understand magnetic nanoparticle dynamics and characterization techniques. This one will be really key through the other two lectures. This is the anisotropy energy. And this says that there is a preferred axis for that macrospin moment, little m, to point along in a magnetic nanoparticle. So I've drawn this diagram here. It's my magnetic nanoparticle that's perfect in yellow again. And here's my macrospin moment. And the dashed line denotes what we call the easy anisotropy axis. And along that axis, the moment prefers to point. So we're going to have low energy if M could point up or if M could point down. And it may come off that axis for a variety of reasons. One of them is thermal energy. It can jiggle off that axis. But if it was only up to the anisotropy energy, the moment would be up or it would be down. Okay. And this anisotropy energy arises because there is an underlying crystal structure for the magnetic material. It can also be imprinted in there when the particles are formed, say in a applied field or so on, but mainly it's the crystal structure. Also, if the magnetic nanoparticles have some shape, then there's a preferred direction as well. But all our cartoons are going to be perfect spheres. So for us, there's some underlying crystal structure which gives rise to an easy axis for the magnetic macrospin moment to point in. We usually assume that this is uniaxial, which is this diagram I've shown for you here. Up or down is preferred. But in many materials, it's actually a cubic anisotropy. And mostly we ignore that because it's too hard to deal with. But sometimes it's important to know that we have a cubic symmetry. So you can imagine 3 easy axes, for example. And as I said earlier, this is key for understanding thermal behavior of magnetic nanoparticles. So we'll see that right now. Okay. So as I said, we've got 2 happy directions here. And so I'm going to take this diagram we saw on the previous slide, and I'm going to plot out the anisotropy energy as a function of this angle theta that we have here. And theta being, this is the angle of the macrospin moment on the x-axis, and on the vertical axis, we have the energy, anisotropy energy of the particle. When we start at 0, theta is 0, that's up, that is low energy because we're along that easy axis. And then in the other direction, when theta is pi, 180 degrees, we're also at low energy. So up and down give us energy minima. And in between, there is an energy barrier for reversal, or an energy barrier to somehow get from up to down. And that height of the barrier depends on the volume of the nanoparticle, V, and also on K, which is the anisotropy constant for the particular material that we're using. And that anisotropy constant has units of joules per meter cubed. So now we can imagine that this macrospin moment could, say, hang out upwards. And there's some energy barrier to get to down. It's not trivial to get to down. Okay. So again, we have a competition between energies, this time between anisotropy energy, and we're going to bring in thermal energy and see how the 2 compete. All right. And the size of the anisotropy energy is this kV. And the size of the thermal energy, some of you might have seen this expression before, is Boltzmann's constant multiplied by temperature. This gives us a feeling for how strong thermal energy is in a system. Okay, so let's start thinking about low temperatures. So if we're at low temperatures, our thermal jiggle is really small compared to this barrier, kV. So you can imagine, say, here's my cartoon again, the macrospin is pointing up when near theta equals to 0. And this barrier just looks huge compared to the thermal fluctuations. Everyone with me on that? Okay. So what do we think can happen to this macrospin? Can it visit down? I have one person shaking their head that I can see. Excellent. That is correct. The one person I can sample is correct. So we get stuck. We say that the moment is blocked. So the macrospin is stuck in this energy well for very long times. The anisotropy energy is just dominating the thermal energy at low temperatures, and we say that the moment is blocked. So you might have read papers where this, blocked nature of the particles is talked about. This is what it means, is that we're at low temperatures and we can't surmount the anisotropy energy barrier. Now at high temperatures, something different goes on. Now at high temperatures, the thermal jiggle, the thermal energy we give our macrospin particles, is much larger than this energy barrier. So the barrier becomes unimportant. And so we have a moment going backwards and forwards, flip-flopping between up and down and all angles in between. So I've tried to draw that with the cartoon here. Over time, the macrospin moment can visit all directions, okay? If we do a time average, or if we average over a lot of nanoparticles, which is typically what we do, we typically find it hard to measure one particle. If we average over time or lots of particles, we get magnetization being 0. But it's not for the reason we saw earlier. Remember, we saw earlier that when we heat up a magnet large enough, above 820 Kelvin, we lose all order. This time we still have order. We still have the atomic moments lined up. There is still some order here, but for a different reason, we see that the macrospin moment can visit all angles, and so we get no net magnetization in a nanoparticle system. So this is known as super paramagnetic behavior, because it's not the same as the paramagnetic state that we saw earlier, but we're still measuring a net magnetization of 0. The onset depends on the size of the nanoparticles you have, and you can see that from this diagram here. The energy barrier is the anisotropy constant multiplied by the volume. So if we change the volume of the particles, we change the height of this barrier, we change the onset of super paramagnetism. I've done a quick estimate. I hope it's correct. I've got for 5 nanometer radius magnetite, this occurs around 25 Kelvin, okay, to give you a feeling. So if we're at room temperature with these particles, they really are super paramagnetic. But if we can cool below 25 Kelvin, then we see a net moment reappear. All right, I think this is our last energy contribution, and then we'll just recap. So this last energy contribution is the Zeeman energy, which is a fancy way of saying the energy in an applied field. So here's my cartoon again, and I've got my macrospin moment, little m. I've got the easy axis, which is the dashed line, and now I'm applying a magnetic field, an external applied magnetic field upwards. And typically magnetic moments want to align with applied fields. So we can imagine the macrospin now coming off its easy axis to try to align with that field as well. So now we have this up direction is going to be preferred compared to the down direction. And so we can draw another diagram of the energy of the particle versus the angle. And it disappeared. And so this is the diagram. Previously, we had 2 energy wells which were equal in depth, and this time the up one is lower in energy, and that's because of the applied field. So we can change the energy landscape of this nanoparticle by applying a field, and the 2 directions are no longer equivalent. And then I've apparently lied to you. This isn't our last energy contribution. We've got one more. This really is the last one, I think. The last one I wanted to talk to you about is dipolar interactions. So we've talked a little bit about stray field and dipolar fields. Let's look at this nanoparticle here in the center, and its macrospin moment is a line pointing to the right, and it produces this lovely dipolar field. And so you can imagine putting other magnetic nanoparticles somewhere in space around this one, and it wants to align, this one say here, its macrospin moment wants to align along that stray field direction, along the applied field direction. So depending where you place neighboring nanoparticles, they want to point in a variety of different directions. This energy contribution is by far the most difficult to treat. And you might get a feeling for that already just from this cartoon, because depending where I put the neighbors, my moment wants to point in a completely different direction. So it's very hard to predict what the dipolar interaction energy is going to do to a nanoparticle, because it really depends on where the neighbors are, how far away they are, and in which direction relative to the moment they are. So this is our most complicated one, and there's still a lot of open questions about how we treat this correctly when we're doing measurements on bulk magnetic nanoparticle samples. If we have particles in fluids, we know they can move around to try to minimize dipole-dipole interactions. So in an applied field, we often get chains, and this is from a simulation we made many years ago. You can see the magnetic nanoparticles form some chain, and if you can see the little green arrows here, that's the macrospin moment in each one. So they're trying to line up tip to tail because that gives us the lowest dipole-dipole interaction. If the thermal energy is too big, the chain will blow apart because we have that competition again between disorder and order. If in zero field, we can see little rings form. Again, this will completely reduce the stray field energy, so that can happen. And then in between, say a weak field, we see all sorts of different configurations happen. So this is just one example. A student of mine called it an end clump. Okay, so we have done 6 different energy contributions of a magnetic nanoparticle, and we will use some of these in the coming lectures. We've done exchange energy, stray field energy, anisotropy, thermal effects, Zeeman energy, or the interaction with an external applied field, and dipolar interaction energy, which I think is the most complicated. So as I said, all these energies will be needed next time when we talk about dynamics and try to understand dynamics. So that's the end of part 1. And I don't think I've gone on too long, so we should have plenty of time for questions.